Let's talk about record merging and linking. These operations take different records, which may be duplicates or they may be near duplicates with similar information, and they establish that they belong to the same record, so that then you can either remove the duplicates or you can just merge them. They usually rely on something called identity resolution, which is how do you establish that two records actually refer to the same entity? And there are multiple algorithms to calculate this comparison. Let's take a closer look at merging, linking, and identity resolution. Merging and linking are two specific types of operations that deal with one specific problem, which is record duplication. They're important to centralize data, especially critical data where the existence of duplicates can have devastating business consequences. These are a staple of activities such as master data management, or MDM, which aims to centralize the core entities in terms of data. So removing duplicates and merging different records that contain parts of the same entity is crucial for this. It's important to note here that duplication doesn't always come in the form of records that have exactly the same content. In some cases, we may have records with similar fields that are equal but in different formats, or that reference the same entity in different ways, such as name versus ID, for example. So you may have a customer that has a certain full name and a certain phone number. You may have a duplicate if you find another customer with the same exact name and the same exact phone number. That's a literal duplicate, an identical record. But you may also have a duplicate which has the same name, but the phone number doesn't include the prefix. Technically, they're different data, but in reality, they're still duplicates. So both types can occur. You may have perfect duplicates, if you will, or just similar ones. And in both cases, there are usually two stages. The first is to link different records to the same entity, and later merging those records. Please note that duplicates and redundant information can come from countless sources, especially in big companies. In companies of large size, you are almost guaranteed to have duplicates of some sort. In many cases, you can never eliminate them all. You can only prioritize the most important ones. But the usual reasons include, first, acquisitions and purchase data. You may buy a competitor who has some clients that overlap, and you have to merge those records. Then, having multiple non-integrated applications where users enter data in parallel, especially if there are weak controls in terms of the information quality. For example, you have 5 different sales and marketing teams all using different interfaces, but working on the same clients. And many of these interfaces don't even allow you to search for an existing customer before introducing data. In that case, you're guaranteed to have duplicates of some sort. Or you may just have a lack of standards in terms of data entry. As we mentioned above, if you have one interface to enter clinical trial data, for example, but you have no way of performing a query and gauging whether a certain trial already exists, then the person inputting the data will most likely create a duplicate, and possibly every single time that they enter data. Now imagine this multiplied by multiple people inputting data. So both linking and merging records usually rely on one activity, which is identity matching or identity resolution, and that is the capacity to compare two different records and conclude that they represent the same entity, or that they don't. At the end of the day, it's a matching algorithm. You give it entity A, entity B, and it tells you whether it's a match or not a match. And naturally, the sophistication of the matching algorithm, together with the actual data quality, defines the quality of the matching. We'll explore this in more detail, but to give you an example, if you compare customer records just by the customer's full name, you're going to get wrong matches because some people may have the same full name. But if you compare customers by the full name plus the birth date, then you will most likely not get wrong matches, because that combination of attributes is more unique. But even then, it can be very rare, but can happen. So the criteria that you use for the matching defines how well you link and merge records. So let's pause for a second and dive into this with more detail. In order to properly perform identity matching, we need to define what attributes are unique to an entity. If you know about algorithms, especially sorting and comparison algorithms, you know exactly what I'm talking about. The attributes that you use for the comparison are a key driver in terms of your results. For example, as we just mentioned, for a person, the attributes that define their uniqueness may be the birth date combined with the full name. That can uniquely identify a person, or the date of birth plus the place of birth, or many others. And when you do the comparison, you compare these elements in specific. For example, if you use the combination of birth date and name, then the identity matching algorithm is going to take two records and say, hey, do they have the same name and birth date? Then they're a match. Are they different? Then they're not a match. I'm naturally simplifying here, but this is the basic process. And as you're guessing, this is also why selecting these attributes is so important. Out of curiosity, for people that deal with databases, you will know that these attributes are usually what generate what is called the primary key of a table. That is, a unique identifier for a given record. And if you think about it, that makes sense, because the attributes that allow you to distinguish a record from any other record in a database are the ones that define its uniqueness. So you can also use them for comparison with others, because if you obtain a match, since they're so unique, then the only possibility is that they're the same record. Therefore, as you're seeing, the process of identifying the attributes which are compared is very important to identity matching. That's why, additionally, in many cases, identity matching can benefit from a bit of parsing and standardizing the data first, so that you can make sure that the attributes are all in the same format. For example, if you're going to compare a customer's first name and last name to match duplicates, you are going to ensure that these names are all in the same format, containing only one word each and no other symbols. Remember, the more unique the attributes are and the higher quality of the data, the better the matching. And also remember that not all data are contained in databases with primary keys. So if you have primary keys, then you probably already know the unique attributes, but you may also need to merge files, logging audit trails, or others. And in these cases, you don't have primary keys, but you can use the same rationale. What are the attributes that uniquely identify every single record? And this is a great segue to the next point, which is when selecting the attributes for comparison, if you have to do it from scratch, there are several criteria here that can make an attribute more or less unique, and therefore make them more or less useful as identifiers for an entity, whether it's one attribute or a combination of these. So if you're wondering, hey, should I use a person's last name? Should I use their birth date? Should I use other characteristics? Or the equivalent for any entity that's not a person? What are some criteria that you can use to select these attributes? The first is the structure of the field. That is, a numeric field, for example, will obey stricter rules than a short text field, which will be better than a long text field, and so on. That is, for example, it's so easy to match numbers. It's a little bit less easy to match a name, for example, due to variations. It depends on the format, and so on. And it's a lot harder to match a long text description, which can vary so much. So the stricter the rules for a field, the better candidate that it is. Then, the completeness and the value distribution of a field also count. That is, if you have a field that is blank in most rows, or in a lot of rows, or that has the same value in most rows, that will not be very unique. For example, if most people are missing the phone number value, then don't use it as a matching attribute, okay? Or if you see that most products in a company come from the same factory, so the column factory is always the same, then the factory may not be a good matching attribute. Then, the presence of the field in other entities also counts. You want a field that exists in this entity and this entity alone, because that makes it more unique. For example, maybe you have an employee entity and a customer one, and the birth date field may exist in both entities. So it's not that unique, but the employee ID field only exists in the employee entity, naturally, so that's a better field. It exists in less entities. Naturally, none of these are absolute criteria. Just because a number has stricter rules doesn't mean it's always better than a string. Just because a value is always filled doesn't mean that it's a better candidate. These are just general indicators, and you have to think about it case by case. Usually, some sort of specialized matching algorithm is used to classify records as belonging to the same entity or not at all. So you throw in a set of records and they spit out the results. These algorithms are usually binary, so you compare two entities and it tells you it's a match, it's not a match, or it's inconclusive, or they may be probabilistic. That is, you input entity A, entity B, and it tells you between 0 and 100% what is the match. For example, these two records are an 80% match. So there are two important things to consider here. First, what to do about the values in the middle. What I mean is that, let's say that we have a probabilistic model, so some records are clearly the same entity. For example, 90% or more similarity, or even 80% or more, and some are clearly a different entity. For example, a 10% match or a 20% match. But what about the others that are in the middle? A 45% match or a 65% match? These may require iterating and refining the algorithm. So you examine the values in the middle and maybe you add additional attributes that can be used to help decrease that middle. For example, this comparison algorithm determined that this product has a similar factory and a similar name to this other one. But they can't be the same ones because the production years are 20 years apart. So you can include the production year in the matching attribute and run it again. Think of it as the following. You have three areas, right? Absolute match, absolute non-match, and then the middle one. And what you want to do is you want to minimize the middle area and you want to expand the other two. A second topic is whether you would prefer false positives or false negatives. The key here is that they always occur. You always have to err on one side. So either you're too conservative or you're too free in your matching. So the question here is, if it comes down to it, would you rather have entities that are considered the same if they're not the same, or would you rather have entities which are the same but are not considered the same? This depends on the context and the criticality of the data. For example, if you're dealing with laboratory data, you may prefer false negatives. That is, you don't want to risk different clinical trials to be considered the same under any circumstance. It would be preferable that even data about the same trial is considered different, and then someone goes in manually and merges it by hand, rather than accidentally considering two trials the same and merging those data, which can have very negative consequences. On the other hand, if you're doing the matching for marketing, for example, and you don't mind the occasional person getting the same email twice, you may prefer false positives. That is, you may prefer to consider leads the same person even if they're not. It depends on the situation and the business goals, but do keep in mind that you are going to have to lean towards one of the two. And finally, an important topic here is the topic of which information is prioritized. That is, in the specific case where you have two distinct records that are clearly about the same entity, but with different values for some fields, for example, two different addresses, which one ends up in the final merged entity? For example, you have two different records for the same product. They have the same code, same original factory, same department. They're the same, but one says the initial production year was 2018, and the other states it was 2019. Now what? Which makes it to the final merged record? This process is called survivorship. That is, which data survive the merging. Or another example, you have two customer records, John Smith living at 17 Oak Street and John Smith living at 27 Oak Street. You're sure that they're the same customer, but you can't verify the address. You're sure that someone must have mistyped the address, but which address remains in the final version? What usually happens is that a good practice in these cases is to establish a ranking of the data sources by quality. This allows a simple heuristic of, in case of conflict between two data sources, you just prioritize data from the highest ranked one. For example, in our customer case, maybe both sales and marketing entered conflicting customer addresses for the same customer, but maybe you know that the marketing department has strict data governance practices and their data sources are classified as trusted, while the sales department may not have good governance. So you can rate the marketing data source as being of high quality, and whenever there's a conflict, their information is the one that survives. What are some examples? The first are internal comparisons. That is, we've talked about the fact that algorithms perform comparisons, but internally they can use several techniques. These include, for example, string comparison, turning all characters into lowercase or uppercase and then counting the letters in common, or edit distances, where you count the number of atomic operations that you would need to perform to transform one string into the other, and then you determine a match if the number is low, or others depending on the data types. But usually, commercial solutions do all of this under the hood. They just ask you, what are the attributes that you want to compare, and they take care of everything. Then, remember that record merging can be in terms of actual records, that is, merging a customer with another customer, or they can merge different parts of a record. For example, changing the sales entities associated with a customer to be associated with another customer, or changing the addresses of someone to be different ones. Or you can even perform both. Or you can even perform aggregation, where you take different parts of an entity and you merge them all together. For example, maybe you don't have a customer entity, but you have customer addresses, you have customer sales, you have customer personal information, and so on. And you can merge parts of all of these to create one single customer entity. And finally, as with other types of tools, such as for parsing and standardization, you can use commercial solutions. But if you have specific needs, you can create a custom comparison algorithm developed internally. For example, if you're trying to compare data in a database table with entities in a file with a different format, and no commercial tool can take care of it, maybe the quickest way is to have some of your best developers just quickly code a matching algorithm using a comparison library, pick the key attributes, and do it like that. What are our key takeaways here? First, to deal with duplicates and redundancy, linking and merging are frequent operations. Linking establishes a link between two records to the same entity, and merging transforms them into one. Then, identity matching. The actual linking of the two records to the same entity relies on identity matching or identity resolution. This is done through a comparison algorithm whose quality depends on the attribute selected. It takes record A, it takes record B, and then it takes the attributes of those two entities, and if they match, it says it's a match, and if they don't, it says it's not a match. Or it detects a probability based on how many attributes match. Then, stemming from the previous point, the selection of the uniqueness attributes for the comparison is crucial for the matching. In general terms, values are good if they have a strict format, if they have unique values that are not empty and not similar to other values, and or if they're present only in that entity and not in other ones. Then, matching algorithms usually either output a match or a non-match result, but we must also deal with inconclusive results, and we must prioritize false positives or false negatives depending on this specific situation. And finally, it's crucial to select what remains in the end. It's very possible that different data sources contain conflicting information about the same entity, and in that case, we must select which information remains. Usually, it comes from ranking data sources and prioritizing the information from the highest quality one. So as we see, merging and linking are all about removing duplicates, and being able to actually resolve two different identities to the same entity is a crucial step. There are many things that help in terms of this operation, such as the quality of the attributes used for the comparison, and also, naturally, the quality of the data.